the navigation subsystem, we've taken our more finalized drivetrain design and implemented that into the kinematics for our simulation. So those are more correct to our final drivetrain design now. And then also we've written some scripts for more automated testing of our simulation. So here you can see we have the set of all of our kind of noise parameters that we want to test our control with, and we're just iterating over them. We kind of initialize the environment and robot with each set of noise and then run the simulation. And here for error, we're tracking the average deviation of the sensor from the center of the line. Here's some output from that. Here we're iterating over area of dirt occluding the line. And you can see up to around 80, which is 0.8 square inches in terms of like the size of the dirt clump is when the robot stops being able to follow the line. For the identification subsystem, we're still waiting on our sensors to arrive. So in the meantime, we started initial gantry integration. So here in the code, we've written up all the code to take input from the webcam and also given some dummy output that will should just be a plug and play thing once the sensors come in. Given that sensor output, we determine the correct location of the asparagus and convert that into the number of steps for the stepper motor and the gantry to spin up. And then we wrote some tests, and you can see over here, this is the output of our test. So we figure out what is the correct position in inches of the asparagus, and then convert that into the number of steps the gantry motor should turn.
This week, Actuator focused on choosing a retaining ring and a foam. For the retaining ring, we found a product that met our 1/8 inch shaft diameter. It does have a thicker profile than the other options we were looking at, but a shaft groove is not required, which minimizes the amount of manufacturing we have to do. For the gripper foam, we found a neoprene foam strip that was 1/2 inch thick and rated at 7 psi. Here are the calculations that helped us inform our decision. Essentially wanted to find the PSI to compress 25% and thickness that would suit our needs. We took into account contact area, input force, desired compression, as well as the thickness required. And the first option we chose had too large of a thickness, so we opted for a lower pressure rating and smaller thickness, which we know will compress at least 1/8 of an inch, but we'll conduct experiments to see if the actual result will suit our needs.
For the gantry subsystem, we just continued work on the prototype, including some building and testing. So this is just the CAD view from last week. So this week we did some loading test of the linear actuator for the Z-axis, and we found that it was able to easily move about 1.5 pounds. And for reference, the actuator is about 1 pound. And then we also looked at some motor selection for the gantry product, including some of these stepper motors here that have closed loop control. And we're still evaluating whether or not closed loop control would be an added benefit compared to the additional cost that we would incur from using these motors. Okay, so for next week, we're just going to continue manufacturing and assembly and try to integrate with both the actuator and chassis subsystems. And for the product, finalize part selection and integrate with chassis.
Hello. So we have a few updates for both the chassis product and the chassis prototype this week. So for the product, we have our CAD. This is integrated with the gantry, and the drivetrain is still being worked on, but there's a lot of progress being made there as well, which Shruti will talk about. And yeah, here's some of the pictures. The middle row are pictures of our product to clarify, and at the top right, we have our prototype chassis. Next slide. Yeah, so for the chassis product, the things we did were the things we want to do are to, one, mount the electronics, two, incorporate the drivetrain, perform FEA, and mount camera, the distance sensors and line sensors, and also mount the basket. For the chassis prototype, we are working on doing most of those things. So for example, the mounts have actually been designed and some have been manufactured, that you can see in the bottom right. And so far all parts have arrived. So build day is actually today, Thursday. So yeah, that's our updates for chassis.
So now hopping on to some updates for the drivetrain subsystem. Initially, we had to make some critical decisions on how we wanted it to look, and this included choosing a drive system of differential drive to actuator motion. And we will have 4 wheels in total, where the front 2 wheels are actuated by a motor, and the back 2 wheels will be free turning with wheels such as caster wheels. So after those decisions were made, we were able to start creating CAD models of how we would like these subsystems to look. So shown on the left-hand side is a picture of how our actuated subassembly of our drivetrain is going to look like. And as shown here, we will essentially have the motor mounted above the axis of rotation of the wheel. And the actuation will be translated through a pulley system between the motor and the wheel/flange subsystem. So we also went ahead and did a rough cost estimate of this entire subsystem. And keep in mind that this is particular to the product, where we have a budget of roughly 30,000 that we're working with according to our market analysis. And per subassembly, we got a total cost of roughly 950. And since we need 2 of these, it would be roughly 2,000 for the drivetrain subsystem, which is a very workable budget chunk for this particular subsystem. Along with that, we were able to choose some caster wheels for the back wheels as shown here from a McMaster part. So our next steps are to integrate the drivetrain components with the chassis and to complete FEA on critical components, the drivetrain subassembly, and the integrated system as well.
Living in the sunlight, loving in the moonlight, having a wonderful time. Having got a lot, I don't